familiar faces here from Tuesday. My name's Dave Pollier, and just to make sure you're in the right place, this is hydrogeology for third year or fourth year undergraduates, and also hydrogeology with independent project for people who are doing masters. So the lectures and the practicals for those two courses will be in common. So just to make sure that you think in the right place, maybe it's compulsory for you, maybe not. But what we're going to talk about over the course of the next 10 weeks or so is hydrogeology, and that is the study of how water underground occurs and how it moves around. And in particular, we're going to look at some of the chemical aspects of that, because one of the major interests, one of the major applications of hydrogeology is in the supply of drinking and other kinds of waters. I'm conscious that we've got quite a variety of people here in terms of backgrounds. So we have several kind of aims for the course. So taking those things into account, and also where people may wish to go to next year. So we're going to look at both aspects of physical hydrogeology and also chemical hydrogeology. I'm far more interested in, for this course, in principles that we might illustrate with specific examples than I am in going into the minutiae of specific examples. And so do bear that in mind when it comes to assessment of the course, particularly on theory papers. It's the principles that we're really interested in. I'm conscious that even in third year, or maybe even at masters, people may still be deciding what it is that they want to go into. So in many ways, this is maybe a rather applied course, and it's a taster course to see if this is the kind of thing that you might be interested in doing. I'm also familiar with some of the hydrogeology masters courses that exist, certainly around the UK, and I hope that this course, it's certainly one of the aims of it, is that it will serve as a preparation for people who might be interested as going on to those courses. And then a third one is that even if you don't want to become, a professional in, say, the water sector, hydrogeology actually underpins a lot of the understanding that we have of many other systems. So there are people here from mineral deposits. This will be useful for mineral deposits. If you're interested in metamorphic processes that involve fluids, it will be helpful. For environmental chemistry, if you're interested in reservoir engineering, petroleum engineering, then equally the principles that we have in here may be very useful. In order to do useful things and in order to make decisions and provide information for people, on the whole, it's useful to be able to describe things in a mathematical way. So the course will have a mathematical bent to it, and it does assume some kind of basic mathematical and some geological knowledge. I won't read all these things out, but for those of you that are particularly interested in assessment, this is what you guys are going to be assessed on. So we have a bunch of intended learning outcomes, and all the assessment that we have, whether it's a practical or a theory or it's a project, somehow is designed to test whether you've achieved these, or collectively we've achieved these. You'll see these are split into two chunks. So the first 6 of those are common to everybody in this room. The last ones only apply to the people who are doing the master's level course. So the people who are doing the master's level course, those I guess mostly on MPEC, will be asking you guys to do a project as well, which will be over and above what the guys on the undergraduate course do. So if you're still deciding, if you have that option, if you're still deciding this is a course for you, these are some of the basic things that we'd expect people to be able to kind of bring to the course. So basic algebra, being able to manipulate equations, being able to use logarithms, exponentials, you can use graphs and functions. I'm conscious there are probably a lot of people here who have not done a geology degree per se. I know some have, but there are many who have not. So for those guys, I think if you're not up to speed on this, it's something that you'll have to do in your own time. I think is becoming familiar with some of the basic rock types and some of the common rock forming minerals. And then the rest of the skills here are largely organisational things. I think, as in any course, we want people to be persistent, careful, thorough, be able to take good notes, and particularly for people doing projects, but this applies to everybody, to be able to look at the literature beyond what I say. I'm just one person. There's a huge literature around hydrogeology out there, and I would encourage everybody to look at that in more depth. So with that in mind, here are some of the books that we recommend for people to read, and also some organisations to look for information on the web. This one by David Waltham, Mathematics, a Basic Tool for Geologists. If you're a person that struggles a little bit with the maths, then this is a fantastic book. It really starts right at the beginning and it's designed specifically for those kinds of people. And most people I know who've read it say that it's very useful for that. If you want a short book that is written by a practitioner, by a guy who's a professional hydrogeologist and has worked for decades in the industry, then this book, Basic Hydrogeology by Michael Price, is an excellent one. And then if you want to go in more depth, then these three books collectively are very good. And the one thing I'd say about these three books, these go far beyond what you are required to know for this course, far beyond it. But I'm conscious that people learn in different ways. The way that I explain things might be good for some people, but not for others. So, and maybe the same way with books as well. So do take a look through these. These are Domenico and Schwartz, Appello and Postma and Feta. They are three classics, but they are written in different ways. And if there are things that you're struggling with in the way that I explain them, then I'm sure one of these books will be able to help you out with that, and also provide theory in more detail than we're going to go through in this course. Okay, so they're the key kind of texts. In terms of what you can find on the web, I'm sure everybody's familiar with the fact that much of what on the web is either irrelevant or wrong. So it's important to have a focus of being able to identify authoritative sources of information. And so for those, there are many more than these, but I would suggest some of these. So the UK Groundwater Forum, they have a whole series of educational slides, some of which I will include in the lectures. And so they're very good to go through to just explain concepts. For data and more detailed information, you can look at BGS, the British Geological Survey, USGS, the United States Geological Survey. We're going to talk later on a little bit about contaminants and regulation. So the United States Environmental Protection Agency website is a useful thing to look at. And finally, IAH, the International Association of Hydrologists, that I gave a lecture for in Delhi last week. So all of those are good websites to look at. For assessment, I know you can read this, but just so that it's clear, and there have been some changes. So for hydrology, for the ART 30182, there'll be two assessments. There'll be a theory exam in the May-June exam period. That's 60% of the marks. And one thing that has changed from last year, I know you may look at last year's exam papers to see what's the exam paper going to look like. This exam paper will look different because for the first time we have only compulsory questions. So I think the questions will probably be rather similar, but the format will be different. So last year it was section A, section B, one question out of two for each. For this one, there'll just be 2 compulsory questions. There won't be any choice. That's not my choice. That's what the university has decided. And then in addition to that, there will be a practical exam. That's worth about 40%. That'll be held in one of our scheduled practicals towards the end of the semester. That will be an open book exam where you can bring all your own notes. So the better notes that you guys write in practicals and also writing lectures, the better place you're going to be to do that practical exam. Okay, so everybody is going to do those. And then for the guys who are doing the master's level course, on top of that, we're asking you to do a project which will be worth 1/3 of your marks. It's something that should take about 50 hours of effort, so like a long week if you like. I'm going to ask people over the next few weeks, and I'll make some suggestions, but you're very welcome to do projects that you are particularly interested in. I'd like those topics to be agreed by the end of February. And then the projects themselves, they have to be submitted by the beginning of May. But if you want to submit them earlier than that, then you're very welcome to. So we're going to do lectures, practicals, self-directed study. And I'd strongly encourage people to go to relevant school research seminars. And there are quite a few, you know, even like Petroleum Group, there are all kinds of metamorphic folks as well. There are a lot of those guys who do research that's relevant to hydrogeology. I'd also highlight, over in chemical engineering, there's a group called Impress, and they hold seminars roughly once a month that are very focused on either experimental studies of fluid flow or modelling studies of fluid flow, both in the crust, but actually more broader applications as well. So a lot of the principles I talk about in this lecture, you can also apply to things like how do you model how blood goes through blood vessels, for example. But all kinds of other applications of it. But it's worth going to those. We're not going to examine those, but it might actually broaden kind of understanding of what you can apply things to. Okay, are people happy with that? Are there any questions? If they're not questions now, just ask me in the practical as well. Do that. So on to the lecture proper, just by way of introduction. So for this, I'm going to go through a bunch of things maybe many people already know, but I just want to make sure that we've got like a firm starting point. So I'm going to talk about these 3 things. I'm going to talk about applications. If you're still thinking about maybe why you should be here or rather than somewhere else, give some examples of applications. I want to make sure that the words we use, the language we use, we understand each other. So we're going to go through some of the hydrogeological terms. And then finally, just a quick review on the controls on permeability of different rock forming units. So the first one, applications. So there are some fairly obvious ones. So water supply is one, modelling seepage from dams, in the mining industry or construction industry, being able to model how fast water will flood mines or flood tunnels. In a few weeks' time, we'll be looking at compressibility and how that controls storage properties of aquifers. And that's actually related to these 2 things as well. The pressure of fluids in the crust near the surface and deeper down are very strongly related to how stable slopes are on the surface, and they're also related to the mechanisms of how earthquakes take place. I've already mentioned reservoir engineering, so whether that's petroleum reservoir engineering, secondary oil recovery, I should put fracking in here as well if you're interested in doing that. or if you're interested in seeing what impacts fracking might have on drinking water aquifers, and similarly, hydrogeology is obviously useful. Waste disposal, remediation of pollution, and genetic studies. So a lot of these are quite self-evident groundwater protection as well. So out of all the things that we require, water, maybe after air, water is maybe the next most fundamental one. We can't survive without it. So water and accessing water has always been very strongly interlinked with power. So the picture I've got here, this is from a stela of this Babylonian king from about 4,000 years ago, and he's handing over one of the earliest known codes of law. And what's interesting from a hydrogeology, from a water supply point of view, is this specifically includes provisions for what to do about people arguing about water supply. So even 4,000 years ago, water supply was really important. This is a picture of a Roman aqueduct in southern France, I think. One of the reasons that the Roman Empire was so successful for such a long time was because they paid a lot of attention to the detail of infrastructure. Maybe it's a standing joke, but they did. They built roads, they organised things, they organised food supply chains, and they also organised water supply chains as well, including the aqueducts. So one of the reasons that the Roman Empire was successful for so long was because they paid detailed attention to water supply. So that is still the case now. Water is still a major issue for many, many countries. And we are also facing the additional concerns that at a time where it looks like we have human-driven climate change, then many of the impacts of that climate change are going to be related to water supply. So to flooding, but also to water supply itself. I've got lots of things in there. I'll allow you people to read all of those. But just to say that this is important, even though it's dripping a bit outside and it's very wet in Manchester, this is actually a problem in the UK as well going forward. So one of the reasons for that is most of the water that we can drink isn't readily available. Or maybe the other way around, most of the water that's around we can't drink. So, most of the water that we see near the Earth's surface is in oceans, which is obviously saline and undrinkable without treatment. We have lots of fresh waters in the ice caps, but nobody lives there, hardly anybody lives there. We can see that much of our surface water supply comes from lakes and rivers. Actually, that's a very tiny proportion of the total water reservoirs. So in terms of drinkable water, the most substantive reserves near the Earth's surface are actually groundwater systems. So groundwater has a huge role to play in water supply, not just in the UK, but many other countries as well. There's one other thing that I wanted to mention. Much of what I say will be, I think, is fairly well established, but some of it isn't. And so for those of you that are interested in the research side, it's worth saying that in hydrogeology, just as in other subjects, there are ongoing studies trying to understand better what happens in these systems. And what the received wisdom today is may be different from what people say in, let's say, 10 years' time. So here's an example of this. I am going to show a picture of the hydrological cycle as we understand it in a minute, but this is what people thought about it about 300 years ago, or 400 years ago. So this is a guy called Kircher, and this is how we reckon the hydrological cycle worked. You had springs up in the mountains, water comes out of those, goes down rivers, ends up in the ocean, and we agree with that. But 300 years ago they found it kind of hard to figure out, well, how does the water get back again? They know lots of sailors had observed whirlpools. So he came up with this idea that, okay, down these whirlpools, that's when the ocean water gets sucked down, goes into these underground rivers, and then that resupplies the water up in the hills. Wow. So you probably look at that and think, that's just ridiculous, isn't it? But these guys didn't know that you can dissolve water in air. So what we understand now for the hydrological cycle, flick through those, this one here, where the hydrological cycle isn't completed by underground water going uphill. Actually, it's driven by the sun. It's driven by heat from the sun that evaporates ocean water, and then we get precipitation over, net precipitation over land. So that's now how we understand this system. And also we have this added complication, but it's a major complication, is that in terms of the hydrological cycle, it isn't all in rivers, it's also in underground flow as well. And even where we have major rivers, like say the Ganges, much of the flow in those areas isn't in the river itself, it's actually in the groundwater systems beneath the river. I said I wouldn't talk about this, but I just want to mention this very quickly for two reasons. One, it illustrates how research works, and also how sometimes doing calculations, we say on the back of an envelope, are quite a useful thing to do. I just encourage you guys to look at this. These were studies done by a French, I guess, hydrogeologist back in the 1600s, and all the calculations he was doing was trying to work out, he was arguably the first person to figure out that all the water that we see going out in rivers actually comes from rainfall. So he did ballpark calculations for the Seine Basin in northern France. This is 300 years ago. And it's a really nice piece of work. You can look at his numbers, they're not perfect, but they're near enough to actually demonstrate that his idea is basically right. That's where most of the water in this basin comes from. It comes from rainwater. So some other aspects of this hydrological cycle are quite interesting. You might think that the diagram that I've just shown, you might remember that from high school. I can remember a diagram like that when I did geography. So you're thinking, well, that's nothing new. So has anything changed? Well, one thing has changed. When I was at school, I came from a place called Tasmania, which is way down here, southern Australia. And we were taught that this is literally true. This is all that happens, pretty much. All the rain that you get when it rains, all the rain comes from the ocean. And I always believed that until a few years ago. I watched a YouTube video of a Dutch scientist called Savanige, I think his name's down here. And I'd encourage you to look at this. And he actually said, no, this isn't true. Not all rainfall comes from the oceans. Actually, a lot of rainfall comes from evaporation from the continents as well. So here's a map, the top one. He's showing in different colours, he's showing the fraction of rainfall that actually comes from continents, not from the oceans. And it's quite interesting in some places, like northern China, West Africa, and parts of South America. They're places that stand out as places where actually most of their precipitation doesn't come from the ocean. It comes from evaporation from continental regions. And you might think, well, so what relevance is that? Well, one of the most important aspects or consequences of that is that these regions are far more vulnerable to changes in rainfall. So in northern China, it's one, and maybe too long ago, but to remember the droughts that were in the Sahel back in the 1970s, largely arose because there were changes in the rate at which water was evaporating from other parts of Africa, from continental parts of Africa. So this cycle, yeah, by and large is right, but actually in detail we are still discovering that there are different aspects to it. That's important. And I can still respect my geography teacher because actually for Tasmania most of our rainfall does come from the ocean, so it's still okay. Right, I'm going to flick through all those. I'd encourage you guys to take a look at that. The other concept I wanted to introduce here is we know about droughts like the Sahel that are caused by lack of rainfall, but we can also have groundwater droughts as well as a result of lack of recharge, and that's something worth looking at. Okay, so there's some of the applications and also showing the relationship with hydrology. So how about some terms? I think most people know these. So aquifers, this is what we technically mean by it. So a permeable unit, which I think most people understand, that's saturated, so that means it's all the pores completely filled with water. And then it also has this part of the definition, that can transmit significant quantities of water under ordinary hydraulic conditions. Actually, right, for those who did mineral deposits, so mineral deposits is an economic term. Aquifer actually also is an economic term because it all hinges on what we mean by significant quantities. Generally, we mean quantities that we can use. So aquifers are typically sands, gravels, sandstones, coarse-grained materials. For the practical that we're going to do this afternoon, we're going to present you with a map of a local kind of geology around Manchester, Macclesfield, and one of the things we're going to ask you to do is on the basis of what we think are good aquifers, where do you think the good aquifers are around Manchester? So then we have other things, an aquiclude, which is incapable of transmitting significant quantities of water under ordinary hydraulic conditions, and an aquitard is quite often used in a similar kind of way, just less permeable beds, and they're typically finer grained materials, or for crystalline rocks, ones that aren't very well fractured. So here's some examples of aquifers, like alluvial fans that have coarse gravels or sands in them. Through these, you can look. Fractured limestones. I put this in to emphasise that permeability can be both matrix permeability and fracture permeability. So, most people might be familiar with the water table, the concept of the water table, but actually it has a technical definition that is important for us to know. So the water table is defined by hydrogeologists as the surface on which the fluid pressure in the pores of a porous medium is exactly atmospheric. So it's defined by pressure. And the zone beneath the water table is the saturated zone. Above it you have the unsaturated zone. And in between you actually have what we call a capillary zone. So just to illustrate that here, this might be something that is the scale of, say, a thin section. So these are all the solid grains. The lighter bits are where there can be fluid in between it. You can see here's the pore water pressure. There's atmospheric pressure. So deeper down in this system, the fluid pressure is greater than atmospheric, and we have a saturated zone. As we go through the water table, the pore water pressure decreases as we go higher and higher up. But actually the water goes above the water table through this capillary zone, the same way that, I don't know, if you put a lump of sugar, if you had a cube of sugar and put it on top of a coffee, then the coffee will slurp its way up through the lump of sugar. It will actually rise above the level of the coffee. And that's due to capillary action. So that happens in groundwater systems as well. I think from a point of view of modelling physical transport, it's not so important. But for looking at where chemicals go, where pollutants go, the capillary zone is really important. And then finally, so it's still 100% pores filled with water, even above the water table. And then finally, as the pressure goes down, we end up with this zone here where we have both water and air or some gas. Maybe in soils you might have high CO2. So we have a mixed gas phase or mixed fluid phase. We have both a liquid and gases in there. So this is just illustrating it again. So later on in the course, we'll be looking at the properties of two very distinct kind of aquifers, and it may seem like just a stamp collecting kind of definition, but actually these two aquifers behave in very, very different ways. So the definition is actually very important. So we have this classification of confined aquifers, which is where the aquifer is sandwiched between two aquitards, and that is in contrast to an unconfined aquifer, or sometimes it's called a water table aquifer, in which the water table is the upper boundary. So here's an example. So this is meant to be a cross-section. This is the surface up here. Here we have clays acting as aquitards. We have a sand aquifer. So this one here, this is confined. The sand, the aquifer up here is unconfined, and water rises up to the water table. Now I've got a new word up here. I've got this thing called the potentiometric surface. So the potentiometric surface is the level to which water would rise from a confined aquifer if it was free to do so. So for example, if we drill a borehole into an unconfined aquifer, then pretty much when we strike the water table, give or take, taking into account the capillary zone, we will strike the water table, and that will tell us something about the tendency of this water to move around. If we drill a hole into a confined aquifer, if we screen this, then depending on what the fluid pressure or the potential for this water to move, then the water will move up this borehole and find its own level. And the surface that we can define by drilling a huge number of boreholes to do that, that's called the potentiometric surface. So when we map these things out, and one of the maps that we're going to show in the practical today is a hydrogeological map of the Cheshire Basin, and it's got some of these potentiometric surfaces on it. It tells us the tendency of water to move from one place to another. So they're really important to know about in order to understand water movement. But importantly, The water table and the potentiometric surface, although, if you like, they're equivalent for unconfined and confined aquifers, they have this key difference. The water table is real. It's like a physical thing that you can detect. The potentiometric surface isn't. It's a hypothetical surface. It's a hypothetical surface that exists even if we don't drill the borehole. So there isn't actually water coming from the confined aquifer up to this potentiometric surface unless we drill boreholes. But nevertheless, we can describe a potentiometric surface for a confined aquifer. So that difference, as it turns out, is really important in how much water you can get out of these different types of aquifers. So another question we're going to ask in practical is just to show where the aquifers we see on a map, where they confined, where they unconfined. So here we have an example of an aquifer where over part of its length it's a confined aquifer, but up here where it's been recharged, it's an unconfined aquifer. So it actually changes from an unconfined aquifer to a confined aquifer. So you can see here the potentiometric surface of the confined aquifer is pretty much equivalent to the water table for where it's unconfined. It's like continuous. And here we have examples of, this would be, the potentiometric surface will tell us if we drill a borehole and we don't pump it, are we going to get water flowing out or not? So in this case, the land surface is above the potentiometric surface, so we don't have a flowing well. We have to put a pump down the well in order to be able to get the water out. Over here, the potentiometric surface is above the ground, so here if we drill a well, water's going to come out all by itself. We don't need to do anything to get the water out. Okay, so for the last few minutes of the lecture, I just want to do a very quick kind of whiz through permeability. And for this week, I just want to cover things fairly quickly. So I'm just going to give a qualitative definition of permeability, which is just simply, it's just how easily water or a fluid can move through a porous rock. In fact, the fluid can move through porous rock. Next week, we're going to look at this in a more quantitative way, and through that we're going to look at Darcy's law, which is one of the ways that we can describe quantitatively how much water moves, how fast through aquifers. So permeability is controlled by a lot of different things. Maybe the most obvious thing for sedimentary rocks or for sediments is grain size. And I'm sure intuitively most people know fine grained materials tend to be less permeable than coarse grain. But it's also controlled by porosity, it's controlled by texture. Particularly in crystalline rocks, it's controlled by the number and types of fractures. In soils, it depends on the degree of saturation. And the two last things I want to say about permeability is that it can often be anisotropic, like permeability in different directions can be different. And unfortunately, probably because it makes our life complicated, is that it's often scale dependent. The permeability on a big scale, I can't stretch far enough, but on a kilometre scale, can be very different from the permeability that you see on a very small scale. So I'm just going to illustrate some of those key points here. But before I do that, sorry, one last really important thing related to permeability. You might hear and might read these two terms being interchangeably used, like permeability and hydraulic conductivity. So actually, permeability is a function of a porous media. It has nothing to do with the fluid. It's a property of the porous media of the rock or of the aquifer. Hydraulic conductivity is a combined property. It's a property of the fluid and of the and of the porous media. Because we mostly talk about water, very often people use these interchangeably, hydraulic conductivity and permeability, but actually they're different things. I think just to simplify things here, I'm showing hydraulic conductivity for water and permeability and comparing them for different rock types. But bear in mind they're different, and in the next few lectures we're going to explain in detail how they're different. So, what are some of the key features of looking at these? You can see these are log scales. So, firstly, finer grained rocks tend to be less permeable. They have lower permeabilities, lower hydraulic conductivities than coarse grained materials. And then over here, you can see here are unfractured igneous and metamorphic rocks. They tend to have very low permeabilities. But here we have fractured igneous and metamorphic rocks. They have much higher permeabilities. So they're already two of the major factors that we can see. You can see that hydraulic conductivity is units of length per time. It's like a velocity. Permeability has dimensions of length squared, and just to avoid having all these horrible numbers, people have introduced a term called the Darcy, and a Darcy is equivalent to 10 to the minus 8 centimetres squared. So unfortunately, just like people talking different languages, hydrogeologists use different units. And when you read stuff, you have to be aware different hydrologists use different units, and you have to be able to translate between them. So you can see roughly what the equivalence is from that. One other thing that's really striking about this, or maybe you might think is really striking about this, is that there is a huge difference in permeability between different rock types. So if you can compare it to a property of, like, say, density, you know, how does the density of rocks change? You know, maybe, like, the lightest thing I can think of is a pumice, which might be a little bit less than 1. The heaviest thing I can think of are maybe some ores, which might be 10 or something. So there's basically an order of magnitude difference in density, and actually for 90% of rocks, it's probably a factor of 2 or less in density. But in terms of permeability, it's of the order of, wow, what is it? A trillion. There's a trillion-fold difference between the most permeable and the least permeable rocks. And that has huge consequences for the way that water moves around in the crust. And later on, in a couple of weeks' time, we will show the influence of permeability contrast on the patterns of groundwater flow, which may be very non-intuitive. Okay, so there are all key points about permeability. So the last few slides I'm going to show is just illustrating some of the key controls of permeability. So I mentioned grain size. So here we have a whole series of sands, I think from the North Sea, and you can see as you go from like clay sands up to coarse sands, for a fixed porosity, the permeability gets higher. That's pretty bog standard. We could also see that for any grain size, the higher the porosity, also the higher the permeability. So it's a function not just of grain size, but it's also a function of porosity. It also depends on how the porosity is interconnected, how well sorted they are. Is there porosity inside grains themselves? And I'll show this one. This is showing what can happen, like diagenetic reactions going on in the sandstone. The scale here is 40 micrometers. So you can see here, or I hope you can, I think these are grains of quartz. And then in the pore throats between these grains of quartz, you're getting books of kaolinite being precipitated. So where they precipitate the pore throats, just a really small amount of reduction in porosity can completely reduce the permeability of the rock. So texturally, this is really, really critical to look at. We obviously mentioned fractures as well. Again, we'll talk about this later on in the course, particularly in regard to chalk. But in some rock types, it's mostly matrix flow, like a whole bunch of grains and water flows between the grains. In other kinds of rocks, particularly crystalline rocks, most of the permeability is through fractures. And it's relatively easy to model matrix-only flow or fracture-only flow. But unfortunately, we also have major aquifers like the chalk, which are both. They have both fracture and matrix flow, and that makes modelling them more complicated. In soils, if you're interested in things that are much closer to the surface, the permeability or hydraulic conductivity is a very strong function of saturation. So you can see here, this is hydraulic conductivity as a function of soil water content. And you can see, again, a very tiny change in soil water content can change the permeability by, 1 million. So if you're modelling this, then this becomes a critical parameter to measure. And then the last two things I want to mention about permeability, and I think you guys can read about this yourselves for more examples and more detail. But the other two things I wanted to highlight, one is permeability is anisotropic. So for those of you who've done, optical crystallography and mineralogy, you're probably familiar with the indicatrix for refractive index for a mineral. You get a rugby ball shaped indicatrix. Well, this is showing the same thing for permeability in a strongly anisotropic rock. So in this one, and it's a good example of one, we've got a lava flow. And so in lava flows, it tends to be that the permeability parallel to the flow of the lava flow can be orders of magnitude greater than the permeability at right angles going across the boundary. And you can probably rationalise that for a lava flow because in most cases you get, rapid cooling of the magma at the margin, so you get very fine-grained, glassy boundaries that are very impermeable. So it's easy for water to flow between those boundaries. We get the same thing in sedimentary rocks, and particularly sedimentary rocks in which there is imbrication, so shales, anything that has a lot of clay minerals, where the clay minerals tend to be, laid parallel to each other like that. Permeability in that direction can be orders of magnitude faster than trying to get across all these flat clay particles. And then lastly, permeability can also depend on scale. And that's really relevant here because we have a group here that does permeability measurements on small bits of rock. So how relevant are they to the larger scale? And these guys are well aware of this. So say for a lava flow, you might imagine that, on a very small scale, the permeability is basically due to the porosity that might have developed between the different crystals. And that might actually be very, very low. On a larger scale, it will depend on the presence of microfractures, maybe as the lava is cooled. When we get to an even bigger scale, that might incorporate the margins of a single lava flow, then that will also change the permeability. And if we go to a much bigger scale, maybe we start encountering things like faults, which might be highly permeable or not. So this is schematic, but just to illustrate that this might be a typical pattern of permeability, where if you're looking at firstly, there is a difference between the small scale and the large scale, but also that you expect much more variability on a small scale than you do on a larger scale. So you can see there's a lot of noise here. If you imagine this is permeability, if you're looking at a micro scale, once we get to a very large scale, much of this noise is flattened out. Okay, so just in summary, hydrogeology is important for a large number of applications. We have looked at a series of hydrological terms. We've looked at the hydrological cycle. We've defined hydrological units. We've got a definition related to pressure for the water table. We have a definition for confined and unconfined aquifers. And we know that in the next few weeks we're going to figure out why that is so important. And then lastly, we've looked at permeabilities on the controls, and particularly also looking at the fact that permeability can be scale dependent and it can also be anisotropic. Okay, so let's finish off there. We've got a 10-minute break. We've got a practical back in the Williamson building, which is G12 and G14. So I'll catch you guys there. Thank you.